طيب, Bismillah ar-Rahim. So as we discussed last time, this is the frame structure for Bluetooth, and we have discussed this frame structure except that we did not cover this small part. So we covered these fields, and we said that these flags are used for flow control, acknowledgement, and for stop and wait. And here, stop and wait ARQ is different from the stop and wait that's used in TCP. Because stop and wait that's used in TCP, if you don't receive an acknowledgement, what do? If you don't receive an acknowledgement,
wait the time until it times out.
And then retransmission, right? Yes. Is retransmission good for multimedia?
No.
Yeah, and that's why stop and wait ARQ is different from TCP stop and wait. So you don't actually do retransmission. So it's different. So we do flow control. Yes, flow control is needed. We do know if there is an error, and we do forward error correction as much as possible. But that doesn't mean that if the forward error correction failed, that we expect to have retransmission, because retransmission will not be necessarily efficient for the case of multimedia. So specifically for one type of connection that we will talk about today, which is the SCO, or the synchronized connection oriented, which is particularly designed for voice transmission. The retransmission will not be used in that case. Okay, so stop and wait ARQ, or automatic repeat request, does not use any retransmission. The other thing is that here we say that this 18-bit header structure is repeated 3 times. So one frame will have 3 repeated headers. And the reason for this is that because we're using forward error correction, sometimes the error is in the header itself. So the Bluetooth uses the maximum type of redundancy in the header and repeats this header part 3 times, so that it uses some kind of majority vote mechanism. So even if some of the bits of the header have changed, then it takes the majority vote. So if the 2 other headers say something and one header says something else, then we know that the majority vote is towards these 2. Okay, so it uses that to increase the error mitigation, or the error protection, when the error happens in the header itself. Okay, so remember that this forward error correction is used for error protection for the data. Okay, but what about the header itself? So for the header itself, we use this majority vote mechanism. So we repeat it 3 times, and if there is any problem with one of them, then we take the majority vote from the other 2. Okay, so that's any confusion here? So that's the mechanism that's used for header error protection, as opposed to data error protection. Okay, for data error protection, we use forward error correction. Okay, so mainly today we need to cover these 2 types of, we call them links, not connections. And pay attention to the term here, because if we say connection, this means that for both of these types, we establish a connection. Whereas we actually have this one is synchronous connection oriented. So in that type of connections, we establish a connection between one slave and one master. So it's a point to point. So for SOC, it's always point to point, one slave to one master. Okay, and it's bidirectional. So when we have a connection, it's a bidirectional communication between one master and one slave. Okay, so in that case, we establish a connection between one master and one slave before we start communication. So that's a circuit switching like operation, in which case the connection will have all the resources required pre-allocated to it. Okay, and as we said before, channel access mechanism uses TDD, TDMA, and these time slots are pre-allocated for the SCO connections. Okay? Whereas for ACL, it's a link because it's not actually a connection in the sense that we establish a connection. Yet it's still logical communication that is going from the master to one or to maybe all the slaves at the same time. So it's generally point to multi-point communication. Okay, so it could be from the master to one of the slaves, or from the master to all the slaves at the same time. So in which case it's a broadcast. So in that case, in this category of on this category of links, we don't actually establish a connection. Okay, so it's a packet switching like communication where the ACL packets get sent before establishing a connection. And here, the time slots are not pre-allocated, right? In which case, we can dynamically change the allocation of these time slots during the communication because there is no established connection that happened beforehand. Therefore, we cannot pre-allocate these time slots. There's no connection, okay? And that's why we call them links in general. So link is a generic term that does not necessarily dictate the fact that you need to establish a connection before the communication. ماشي كده? So a link, and that's why the module that you talked about is called a link manager. It's not a connection, it's a link manager. So link manager establishes communication between the master and the slaves in general, in an SCO mode or ACL mode. Okay? So now, because SCO is a bidirectional communication, so we need to have some, so there is for sure some limitations on how many connections we can have concurrently running. And it turns out for SCO, one slave could have up to 3 different SCO connections to the same master. Okay? And this is a bidirectional, point-to-point bidirectional communication. So one slave could have 3 connections concurrently running to one master, to the same master, which means that it's in the same piconet, right? If it's on 2 different piconets, in which case it's a slave that is part of 2 different piconets, then this actually drops down to 2. So you can have one SCO connection to one master and another SCO connection to another master. But if it's the same master, you can have up to 3 connections. Okay, 3 concurrent connections. If there's 2 piconets, this means that this slave is part of 2 piconets. Okay, in which case it can have one SCO to one master and another SCO to the other master. It cannot have 3 in that case because it's 2 different piconets. Or maybe 2 SCOs to one master, but it cannot have a third one because it's connected to 2 different piconets or 2 different masters in that case. So it's the condition for 3 concurrent SCO connections is for the same master. Okay, so this is from one slave. However, the master can have also up to 3 concurrent SCO connections in total to any slave, which means that if one slave has 3 concurrent SCO connections to the master, then it's the only slave that has 3 concurrent connections to that master. All the other slaves can have ACL connections, but not SCO connections. Okay? So it's 3 because it's SCO is by default bidirectional. Okay? So the master cannot have more than 3 concurrent SCO connections, and the slave cannot have more than 3. But if a slave has 2, then another slave could have 1. Okay? If each slave has one, then the master can connect to 3 different slaves using SCO. Okay? For the case of ACL, each slave, because it's not a connection. All the ACL traffic is actually scheduled through one big ACL link. We don't call it a connection in that case. So it goes through one ACL link. Okay? And usually this is the it's the other traffic other than voice communication. So data communication all goes through ACL. For ACL, you can use retransmission in that case. There's no problem. Okay? SCO does not use any retransmission, although it uses flow control, although it pre-allocates all the time slots and everything, but it does not use retransmission because this is not efficient for multimedia communication. Okay? So, yeah.
I've got a question. Now you said one slave could be part of 2 different piconets.
Right.
So how can it differentiate between the 2 kind of picconets? For example, if you have usually one device that has a Bluetooth, you connect it to other device, and then you have just that kind of connection going between them, but you can't connect one device to 2 different nets.
Yeah, as we said before, this is the only way for us to have long-range communication. Okay, so you can communicate to one master, and then the master could communicate to a slave which is part of another piconet, and then the slave could communicate to the master in the other piconet, and then from that master to the slave in the other piconet. Okay, so that's the only way. So it has to go through multi-hub. Okay? So this is the only way for us, because other than that, Bluetooth is very short range. So but you could have the standard actually defines a way to increase the range of communication, but that has to go through multi-hub. And as we said before, Bluetooth does not support slave-to-slave communication. All the communication has to go through the master.
So who decides which one is the master and which one is the slave?
Yeah, the nodes themselves, they nominate one of them as the master node. So the master node is designated, or in some cases elected, throughout the communication. So if there are 2 nodes that start communication, the first node that starts will act potentially as a master node, and then the other node will connect or pair with that, in which case it's a slave. If another slave comes in or another standby node comes in, then what happens typically is that this standby node will listen to all the broadcast piconet IDs, okay, which is usually broadcast by the master node in that piconet. And then the standby node may actually choose to be part of this piconet, in which case it will connect to the master node. But as we said before, up to 7 of these active nodes can be associated with the master node. But all the other nodes can still be part of the piconets, which is what we refer to as parked nodes. They can be part of the piconets, but they are in a parked mode, which means that they are not active, they are not communicating anything. But the standby node is totally not associated to the piconet. Okay, so as we said, so one slave can have up to 3 concurrent SCO connections, up to 3 concurrent, and 1 ACL link. Okay? So the master itself can have 3 SCO and up to 1 ACL link per slave. Okay? So in total we could have 3 concurrent SCO and 5 different ACL links to 5 different slaves. Okay? This is from the master point of view. But from the slave point of view, it's maximum 3 SCO connections and 1 ACL link. Okay? As we can see here, in this graph, the SCO number 1 connection has allocated time slots to it. Okay, so these time slots are pre-allocated to this SCO connections. Another SCO connections, SCO2, for example, could have some allocated time slots for a specific node. Okay, so these time slots are pre-allocated at the beginning of the communication. Any other time slot can be allocated to all the other ACL lengths dynamically throughout the time. Okay, but they are not pre-allocated, which means that implicitly what we are doing here is that we're giving more priority to SCO connections more than the ACL lengths, right? Because later on we'll talk about the scheduling mechanism. So in a way, this is a strict priority queuing. Because right now we have higher priority to the SCO connections versus ACL lengths. So first we pre-allocate all the time slots, and this will have to be served. Will have to be guaranteed and served. Okay? And then all the remaining time slots, they will be allocated dynamically to ACL. It turns out that one of the ACL links is used for control. So one of the ACL links is separate and is used for control. So when we say a slave can have one ACL link to all the data traffic, this is excluding the control packets. The control packets are sent on a separate ACL link. Okay? This link actually has higher priority than the actual data ACL link. Okay? So it's actually, that's why I'm saying it's a strict priority queuing. The highest priority would be for SCO, and then the ACL control link, and then the ACL data link. Okay? So with that, of course, the question is, can we provide, what type of quality of service we can provide? Quantitative, qualitative, what is each of these link types can provide in terms of quality of service, whether it's qualitative or quantitative?
NSC to be more quantitative.
The what? The SCO, right. So for synchronous connection oriented, we can provide guaranteed quality of service, quantitative. So we can guarantee delay, for example. We can guarantee specific throughput, specific dropping probability, something like that. Because all these time slots are pre-allocated from the beginning, and it's deterministic. So we know exactly how many resources, how much resources are allocated to this connection before it actually starts. So this way, we can predict or estimate the delay and the throughput and everything, and then we can provide some guarantees on the quality of service. ACL on the other side is not as such. So for ACL, you can provide differentiated services, and we'll see how now. But in terms of guaranteed quality of service, ACL is not efficient in that, because all the traffic is going through one link, so we cannot actually, we cannot distinguish between them. And also, we allocate resources dynamically throughout the time, so we cannot really guarantee how much delay and how much packet loss and so on the ACL links. Okay? So, since we started talking about quality of service support, so we need, as usual, to try to see how the classification is done, if we have channel access mechanism and what it is, and what is the scheduling in terms of intra-packet scheduling, inside one slave or one node, how's the scheduling is done, and if there is any inter-slave packet scheduling, and so on. Okay? So basically, the classification is done through the logical link control and adaptation protocol layer. This is the first layer, as we said before. This is the one that maps the application level requirements into the lower layer services in terms of SCO versus ACL and so on and so forth. So this is the first layer that takes the requirements of the application, and for that it uses some kind of higher level signaling. Okay, so there are two different signaling levels as part of Bluetooth. There is the signaling which is done as part of the logical link control and adaptation protocol layer, and there is the also the signaling that's done as the at the link manager level. So here, this level, as I said, maps the application level requirements into a specific lower layer services. So it takes the requirement from the application layer, and actually this is the first for the first time we talk about this. This layer actually implements token bucket shaper, because as we said before, for all the other standards that we talked about, they do not actually provide application level details. Okay, so they don't care so much about the application level details, because these standards are mainly designed for core networks. So they deal with the traffic as generic traffic that is coming to the core network. Bluetooth, on the other side, is not for core network, obviously. It's for personal communication. So it's for edge networks, and that's why the application services affect the functionality of Bluetooth, because it supports voice, it supports data, and so on. So discussing the specifications for the application level profiles is actually included as part of the standard. And that's why we talked about different services, starting from emulating serial communication and human interaction devices and TCP/IP applications and so on. So there are some diverse set of services that can be accommodated through Bluetooth. So that's why logical link control and adaptation layer tries to do some packet segmentation and restructuring to these application level services in order to fit with the lower layer services in terms of links, SCO versus ACL, and so on and so forth. Okay? So basically, as you can see here, all the connection IDs that are coming from the application in terms of data communication, they all go to the same ACL link. Okay? So this is a type of classification. So if it's voice communication, then all the connections will go to one of the SCO connections. So you can have up to 3 if you want. So one slave can have up to 3. So there could be some kind of separation, but for all the data communication, it all goes through the same ACL link. Okay. So this is some type of classification that happens in the logical link and control and adaptation sublayer. Okay. Then there is the quality of service signaling at the link manager, and that's another level of quality of service through which the nodes may actually request certain resources from the master. Okay, so even the ACL links, they can request certain resources from the master node, and then the master node can then grant this request or not. So there is some kind of a bandwidth request that happens at this layer. Okay, so there is application level signaling, and there is link manager signaling through which the nodes may in fact request some bandwidth requirements as well, and based on that, the master node will use these bandwidth requests to allocate the different time slots. So this signaling may happen at the beginning of the communication for the SCO case, and then the master will pre-allocate these time slots, or it could happen during the communication for the ACL lengths, in which case the master node will change the pooling sequence or the allocation of the time slots, as we will see in a minute. Okay? So based on this level of signaling, the master node will now get information about the quality of service requirements of the nodes in details. Based on that, as we said, for the SCO links or the SCO connections, the time slots are pre-allocated. So that's خلاص, they are pre-allocated from the beginning of the communication. Okay? So that's done. It's fixed throughout the communication. It's fixed. So we don't change that. But all the other time slots can be allocated, okay, dynamically to the ACL links. So how is this done? This also uses a pooling mechanism. Okay? So the master node will pull a certain slave to send data in the uplink. So in the downlink, the master, as we said, all the even time slots are allocated to the master node. So the master node in the downlink will send data to a specific node and may actually use that to pull a specific node to send data in the uplink. Okay? So this is, in that case, this is a unicast pull. So you send a pull to one of the slaves to send in the uplink. So this pulling signal, that's why it's one of the signaling messages. This pulling signal will control a specific sequence to pull all the slaves, and depending on this sequence, we can provide variable type of quality of service, which in that case would be mainly qualitative quality of service, which means that we can provide differentiated services between the nodes, but we cannot really provide quantitative quality of service. So quantitative quality of service is mainly for SCO connections. Okay? So depending on that pulling mechanism, or the pulling sequence, we can give more priority to one slave over the other. So basically, this pooling sequence controls the interstation packet scheduling. Okay? Because the master will control which slave will be scheduled first based on sending specific sequence of pulling messages to the different slaves. Right? So this is the interstation packet scheduling. So I control the interstation packet scheduling based on the pulling sequence. So there is we cannot map that to one of the scheduling mechanisms that we have studied. So we cannot say this is weighted fair queuing or strict priority queuing, because it depends on the pulling sequence. So I can schedule these slaves in any scheduling discipline I want. Okay? But the intra-station packet scheduling, if we look at this slave inside it, who will go first, or who will go second, or what is the scheduling mechanism? As we said before, the SCO connections will have more priority in a way because all the resources for these SCO connections have been pre-allocated. So the time slots for these SCO connections are already reserved, which implicitly indicate that the SCO connections will have higher priority. So the intra-station packet scheduling is strict priority queuing. Okay? But the inter-station packet scheduling is dictated by the pulling sequence. We don't know. Depending on whatever pulling sequence we use, we can change that scheduling. We can give more priority to a certain slave over the other. Okay? We can make it strict priority if we want. So we can say slave 1, for example, all the packets that are coming from slave 1 will have to go first. In which case, the polling sequence will enforce a strict priority queue. But in general case, we don't know. It depends, and this is not part of the standard, so it's up to the vendor to select whatever polling sequence it finds appropriate for a certain application or certain environment. Okay? So then we talked about classification from the application layer. We talked about channel access mechanism, which is obviously in that case it's TDD, TDMA. Okay? So we actually, but as we said before, here the subframes are mixed. So all the even time slots are allocated to the master node, and the odd time slots are allocated to all the slaves depending on this polling sequence bar. Okay? So the channel access mechanism is TDD, TDMA, which means that it's collision-free. There's no collision in that case. And the intra-station packet scheduling, as we said, within one slave is strict priority queuing. Between all the slaves, it depends on the polling sequence. And for signaling, as we said, we have two types of signaling, or two levels of signaling, which indicates that we have explicit signaling mechanism for Bluetooth, which gives us the indication that if we want to have explicit admission control, again, we can in that case, because we have explicit signaling mechanisms. So we can decide whether or not to admit one slave to the Piconet or not, which is what we refer to as a explicit admission control. So again, the explicit admission control mechanism itself is not part of the standard. However, it's facilitated by the fact that we have signaling mechanism. Okay? So just the fact that we have signaling mechanism will enable us to have explicit admission control. However, there is no actual admission control mechanism defined by the standard. Okay? Any other thing on this? Okay, I think we're done. So any questions here? Okay, so basically the standards that we talked about, I can classify them broadly into like two schools. Some people, they took the school of collision-based channel access, where they, in a way, they believed in the fact that through a random environment where everybody is actually contending on the channel, we can have more efficiency in that case, which has some advantages and disadvantages. And the Wi-Fi group has actually pushed for this, throughout the history, and it looks like it's living up to the moment. So nobody actually thinks about ignoring or removing Wi-Fi anytime soon. Even with the proliferation of 5G and things like that, nobody actually expects Wi-Fi will go away anytime soon. But that doesn't mean that Wi-Fi does not have challenges. Of course, as we have discussed throughout the course until now, that this random environment of having collision, although it has some advantages, because for DCF, as we said, we don't have to have a centralized coordinator, so it's distributed in nature. So this might be an attractive feature. However, it introduces many other challenges, and one of them is for quality of service. As we said, for this random environment, we cannot, by any chance, provide guaranteed quality of service. Because the collision-based environments will always have this random collisions that we cannot control. Since we cannot control, we cannot estimate or predict. And this way, we cannot really provide guaranteed quality of service. For the two set of standards, because they have been designed originally with some multimedia in mind, so they decide, because metropolitan area networks was originally designed for voice communication, and Bluetooth was originally also designed for mixed between voice and data. So this school has actually advocated the collision-free environment, in which case, although you have some kind of overhead, because as we said, these time slots require some synchronization, and you need to have some centralized control to assign these time slots dynamically, so we know that. So that introduces overhead. However, as we discussed, this will allow us to provide some guaranteed quality of service whenever we want. So we have the option to provide quantitative quality of service to multimedia applications if we want. Okay? So any questions? All right, so inshallah on Tuesday we'll have the review.